So now the height of the left minus height of the right means height of the left subtree of that particular node minus height of the right subtree. So for this particular node, which is the tree node, I mean the root node, so we have uh, this is the left subtree for this node, and this is the right subtree for this node. So the difference between height of the left subtree minus height of the right subtree is 2 minus 2, which is equal to 0, right? So if I quickly write the differences for all the nodes, it looks something like this. So for this tree, for this node, the difference in the height is 0. So for this node, it is 1 minus 1 again, height of the left subtree minus height of the right subtree. So it's equal to 0. So it is 0. So if I calculate for this, it is 0. Like, what is the value of it here? So in this case, we are getting 0 minus 1, right? So the value is minus 1. So we will not have negative values here. You need to calculate the modulus. So if it is a negative value, you need to take the modulus of that. So in that case, it is equal to 1. So I'm just taking modulus of this value. It's not it should not be a negative value. The difference should not be a negative value. It should be a modulus value. So here I am taking it as modulus of height of the left minus height of the right is the one that we wish to do. So that's the reason here it is 1. And if I go here and calculate for this, it is 0. In a similar manner, the value of it is, this is 0. So for this node, there is no left subtree and right subtree, so the value will be equal to 0. So for this, the value is equal to 0. And for this, again the value is equal to 0. And for all the leaf nodes, the values will be equal to 0. So these are the values that we will get when we calculate the modulus of height of the left tree minus height of the right tree. So if I go for this tree and if I calculate for them, so the value of this node will be equal to 0. What will be the value of this node?
1.
It is 1 minus 0. So is it
1.
1 minus 0? Yes, it is. Let me add one more node here. So that, so the height here will be equal to, so let's recalculate it. So what will be the height of this one? It will be 2, right? It will be 2. And what is the height of this one? It will be 1 and it
1.
will be 0. So this will be equal to 1 and this will be equal to 0. So now if I calculate this, so this becomes 2, so this becomes 3, so this becomes 3, This becomes 4. This becomes 4. So now if I calculate the differences between height of the left minus height of the tree, it should be equal to 1 here. And what will be the value here?
1, 3 minus 2.
It will be equal to 2, right? 2 minus 0.
Okay.
It doesn't have any left subtree, so the value will be 2 minus 0. So the value will be, so the difference between height of the left minus height of the right will be equal to 2. So what will be the value of this?
1.
So it will be equal to 1 minus 0, it's equal to 1. For this,
0.
for this,
0.
yeah. So for all the leaf nodes, it is equal to 0. And for this, it is 1 here. And here it is equal to 0. So 0.
0.
Yeah. So now if I look at this, both the graphs, the condition that should be satisfied for a balanced binary tree is, so we are talking about balanced binary tree. So we can call a tree as a balanced binary tree if modulus of height of the left minus height of the right should be equal to number of edges. I mean to say, it cannot be more than 1. So if the height of modulus of height of the left minus height of the height of the right is greater than 1, then we can call that graph as not a balanced binary graph. This value should not be greater than 1. So if you observe both the graphs, the left side graph, the maximum value that we do have is 1. So for any graphs for which the height of the left minus height of the right is maximum 1, then we can call that graph as balanced binary tree. I mean, we can call the tree as balanced binary tree. And for any graph whose height of the left minus height of the right exceeded 1, we call that as not a balanced binary tree. Like we cannot consider that tree as a balanced binary tree. So that is what we need to calculate to decide whether a tree is a balanced binary tree or not. Okay, so this is one of the kinds of trees. uh, we have discussed this. Now moving forward, just a quick recap on all the trees that we have discussed till now. So can someone just recap all the topics that we have discussed in trees till now? Hello. So let me do that. So in trees we discussed different terminologies that we use in trees, and we have studied what a tree is, and different terminologies associated with the trees. And then we calculated we studied what is the depth and height of a tree. And also we have looked at different categories that are there in the trees. So we learned what is a binary tree, and different types of binary trees, like strict binary tree, complete binary tree, and perfect binary tree. And we also calculated the heights of a node in a perfect binary tree, a maximum number of nodes at a particular level, and maximum number of nodes up to particular number of levels, like height of the perfect binary tree with n nodes, maximum number of nodes in a tree with height h. So these two formulas we did calculated, and then we studied balanced binary tree now. So it's nothing but differences of height of the left minus height of the right. uh, the modulus of height of the left minus height of the right should not be greater than 1. It can be max of 1. So still here we covered most of the topics in trees, and now we need to understand binary search tree, and which is the most important tree that which will help us to do the bus searching techniques, like if you want to search something in a particular tree or in a particular list, this helps us a lot. So what is binary search tree is, it's a special kind of binary tree. When I'm saying binary tree, it can have maximum of it should have only 0 to 2 nodes or subnodes under it, under a node. So binary search tree is a special kind of binary tree which is an efficient structure to organize data for quick search as well as quick update. So this binary search helps us to do a quick search on the list of items that we do have. So for that, so before going forward with binary search tree, let's calculate the time complexities and space complexities for different searchings. So let's say I'm given an array, and if I want to search for an element in the array, what will be the time complexity? So let's say I'm given a list of items, 12, 45,
Order of
89,
n.
6, 3, and so on. So now we are calculating time complexities. So for array, what is the time complexity to search an element? Let's say I want to search 89 is there in this array list or not. So what will be the time
Order of n.
complexity? Sorry.
Order of n.
Yes, it's order of n, right? Okay. In a linked list,
Order of n.
order of n. So it is order of n. So in sorted array,
Order of n only.
order f,
N.
no, like if we have a sorted
If
array
you
in
know the
this,
index, then it is okay.
yeah. So we can do this way, right? So when we are discussing the merge sort, we have somewhere like, if I have a sorted array like this, 3, 6, 7, and what is the next, 12, 45, 89. So if this is a sorted array, if I know the array is sorted, can I do this way for search an element? Can I take the middle of the element, and can I compare with the element with which I want to search? I want to search for, like, 89 is the value which I want to search, and I'll take the middle index and I'll search like whether 89 is greater than or less than this middle value. If it is greater than, I need to search only in the less in the right portion. If it is less than, I just need to search in the left portion. So now with this logic, how the value in how many values we are comparing it. So instead of comparing in n values, we are just doing uh, the comparisons in only n by 2
P2.
values now. So instead of the whole array, we are only searching in half of the array, if we know the array is sorted. In the similar manner, again for the sub array, I'll iterate again and I'll take the mid value. So in this array, the middle value is 45, So again I'll check whether the value is greater than 45 or less than 45. So again I'm reducing the total number of elements to n by 2. So if you are decreasing the values by n by 2, so what is the time complexity? It is equal to log n, right? Log n to the base 2 will be the time complexity, as in every round of iteration we are reducing n by 2 elements in the list or the array. Am I correct?
Yes.
Yeah. So for a sorted array, the time complexity is equal to log n, order of log n to the base 2. Now tell me, what is the, this is for search, right? This is for searching an element in an array. If I want to insert an element in an array at a particular index, what will be my time complexity?
Should be the same, log n.
Yes. Is it log n to insert an element in an array?
And the
So for example, I want to insert at a particular index n. Let's say I want to insert at index 2. So what I need to do, I need to move all the elements to the right to the next indices, right? Am I correct?
yeah.
So let's say in the worst case, if I want to insert the element at 0th index, do I need to move all the elements to the next to all the elements in the array to the next positions? I mean, I need to move the array at element at index 0 to element at index to index 1. In the similar manner, I need to move all the elements. And for calculating time complexity, we do need always consider the worst case. So here the worst case is inserting an element at index 0. So in that case, we need to move all the elements in the array. So all the elements in the array, moving all the elements in the array requires traversal through all the elements. So traversal through all the elements is nothing but it's a for loop starting from index 0 to n. So now what will be the time complexity?
O of
Order of
n.
n.
Of n. So for linked list,
I think for that order of one only, because we just we give the pointers only.
right? So for linked list, it's nothing but we'll just modify the uh, links that we have for the different values. So it is equal to constant time complexity, which will be equal to 1. So for sorted array,
Order of n, because if you want to add something, then it will be order of n.
yes. So now what will be for remove?
Same order of n. You have to traverse through the array.
Yes. So for linked list,
Order of constant one.
is it constant?
Yes, sir. Because we are just removing the pointers and pointing to the next.
And if you are removing something, let's say you're given to remove an element 45. For that you need to search it, right, where it is. If it is matches, then you can remove it.
Yes, yes, yes. So then order of n.
So for sorted array,
Order of n only.
order of n. So if you see all these values, order of n is not a good value in complexity chart, right? We go complexity chart, order of n is not a good value. So only for sorted array it is logarithm of n. So it's something good value. Like if I take, let's say 1 million records. So for each traversal, if it is taking some nanoseconds, so you know the all these calculations, right? Order of n basically takes a long time, and it's an worst algorithm. I mean to say, it's not a best algorithm. Whereas logarithmic n is something that is that can be considered as a good algorithm, because if I traverse through 2 to the power of 100 times, it just takes only 100 uh, 100 amount 100 units of time. Even if it is 2 to the power of 100, it takes only 100 units of time, because it's 2 to the power of 100 to the base 2 will be equal to just 100. So this can be considered as good, but rest are all not a good algorithm. We cannot consider rest of all as a good algorithms. So if I have something like, let's say, I'll call this as, let's for now I'm just writing this balanced binary tree. Balanced binary search tree. So for balanced binary search tree, all these values, like for insertion, deletion, and removal, we have the same time complexity, which is logarithmic n. For all the values, we have the same complexity, logarithmic of n. So it will be equal to log of n. So balanced binary search tree has logarithmic time complexities for all search, insert, and remove operations. So can we overrule all these things, and can we start using binary search tree for doing this search? As it can we consider that, because it has the logarithmic time complexity for every operation that we basically perform. So can we say that binary search tree is something that is most feasible when we have huge number of records and we want to search in those records?
But the sorting will take more time for that many records, right?
Yes, let's
It has
say
to be
yes.
sorted.
True, it has to be sorted. But if we are storing the records, when we are storing the records, if we are maintaining that sorting hierarchy, so when we are storing the elements, it's into the list itself. If you are storing that in a sorted manner, will that work out? So if in a linked list, your linked list dot add, you are doing it. So you don't know how it is storing. It's like it will be storing somewhere, and that will be assigned to the last node, or to the index at which you want to tag. But in the similar manner, uh, if you doesn't need to specifically sort the list, and if you're doing it, will that work out?
Should work then.
Yes, hope you understood. So when we are storing the elements itself, we are doing something like we are storing it in a sorted manner. So we are making sure the list is not disturbed, and it is in it is still in sorted order, even if you're adding a new element to it. So that's we do in that's we basically do in balanced binary search tree. So this is just to show you, like, balanced binary search tree will have the best time complexities when compared to any other things that we do have, like array, linked list, or sorted array. So let's see what is a binary search tree, and how do we do search and insertion, deletion, and all this stuff in a binary search tree. So let's move here and see. So if coming to the definition of binary search tree, so in a binary search tree, value of all the nodes in left subtree is lesser or equal, and value of all the nodes in the right subtree is greater. So if you have a node, and for that node, or let's consider the root node, to all the nodes which are on the left side of to this root node should have lesser values than the root node, and for all the values which are on the right subtree should have greater values. So let's quickly take an example and see this. So I have 15 here. 15. So all the values which will be on the left side of it should be less than the values on the should be less than the value in the root, and to all the nodes which are on the right side should have more values. this is my tree. So it is 20 here, 17 and 25. So let's consider this as my tree. So this is my tree. If you basically see this, so my root node is 15, and all the values to the left of this root node should be lesser than 15. So if you consider all the values here, 10, 8 and 12 are lesser than 15 values, and all the values to the right of it should be more than 15. So if you see this, 20, 17, 25 are greater than 15. So if you consider this node 10, so all the values to the left of this 10 should be less than 10. So 8 is less than 10 and 12 is greater than 10. So if you consider this subtree, so the root value is 20, and to the left it is 17, so it's 17 is less than 20 and 25 is greater than 20. So it satisfied the condition that we are talking about. All the left subtree values are lesser than the root, and all the right subtree values are greater than root, and it is satisfied at each and every level. So we can call this as binary search tree. So now let's say if I want to search a value in this binary search tree, can I traverse this way? Let's say if I want to search 12 here, can I traverse this way? So I'll compare with the root node, and I'll check whether the value is greater or lesser than this. So if it is lesser than, I know I need to traverse on the left side, because in binary search tree the basic the prerequisite is, so all the values lesser than the root has to be on the left side, right? So that is the prerequisite. So now I want to search 12 which is lesser than the root value, so I know like I need to traverse only on the left subtree. So it's like reducing, we are reducing number of elements from n to n by 2, right? So what we are doing it, so we are searching an element called as 12, and we are checking that with the root node, and if it's lesser than the root node, we are traversing only in the left subtree. If it is greater than 15, we just need to traverse only on the right subtree. So we are excluding all the elements in the left subtree if you are traversing in the right subtree, and we are excluding all the right subtree elements if you are traversing in the left subtree. So it is nothing but we are excluding n by 2 elements, and we are considering only n by 2 elements for the searching, right? So if I come down and I need to check this value now, this will be my node. I traversed from 15 to 10, and again at the 10 I'll search like whether my value is greater than 12, my value is 12 and my value is greater than 10 or not, or less than 10 or not. So if I check that condition, if 12 is greater than 10, so I need to traverse only on the right subtree. Because any values greater than 10 will be there in the right subtree, not on the left subtree. So in that case again I'm excluding n by 2 elements. So from n by 2 I'm excluding another n by 4 elements, and I'm searching only n by 4 elements. So what will be the time complexity for this?
In log n.
Yes, it's log to the log n to the base 2, right? It's logarithmic time complexity. Am I correct?
Yes.
Yeah. So let me take another example, and so it is 15, 10, 8, 16, 20, 17, 25. Is this a balanced binary tree?
No, sir. Because yeah, in the left subtree there is the value 16, which is greater than the root 15.
Mhm. So 16 is greater than 15, which is which where the prerequisite is not achieved, so we cannot consider this as balanced binary tree. So for balanced binary tree, we cannot achieve logarithmic of n or time complexity for searching factor. So only for the balanced search tree we can achieve logarithmic time complexity. So before going further, you need to make sure like the tree that you are searching is uh, binary search tree. So for only binary balanced search trees, we can achieve logarithmic time complexities. So let's say I have another tree like this. So is this a balanced search tree?
No.
No. Why?
Because it's linear.
Linear. So what is the condition that we need to check for check whether a tree is balanced search tree or not? So to all the values which are on the left side of the node should be less than the value of the node, right? That is what we has to check. Am I correct? Hello. So if I do that analysis, like this is my root node and all the values to the left are less than the root node. So all the values to the left, which is 10, 12, 15, 17, 20 or less than 25. So there are no right values, so we doesn't need to bother about them. So again if I consider 20, all the values to the left of that node or the left, all the values in the left subtree are less than the value 20. So 17, 15, 12, 10 are less than 17. So for every node the left subtree values are lesser than the root node, right? Or let's say it's not the root node, the left subtree values of the particular node. So at every stage or at every level it is satisfied. So we don't have any other requisites like prerequisites that needs to be validated. Only prerequisite that needs to be satisfied for a balanced search tree is values in the left subtree should be lesser than the root node. That's the only thing. So it is satisfied here, right? So it should be a balanced search tree. Sorry, it is a binary search tree.
Yes,
Is
yes.
this a sorry, someone is asking. So is this balanced or not? What did I ask? Whether asked it's a binary search tree or balanced tree?
You asked for a balanced tree, sir.
Okay, so is this is not balanced, right? That's yeah, that's correct. So this is binary search tree, but it is unbalanced. It's not balanced. So this is a binary search tree, but this is unbalanced. So we can achieve logarithmic time constants only for balanced binary search trees, not for unbalanced binary search trees. Balanced binary search trees. So can you say me the time complexity of this particular tree?
For search operation?
Sorry, order of,
For search operation?
yes, for search.
No. Log of n?
No, it's not log of n.
Order of n?
Yes, it's order of n. Can you tell me why?
It's linear because it has to traverse through all the elements. That's why.
Yes. So there is no chance, like it's something like a linked list. So we have all the elements, and we have all the elements in a single hierarchy, and so we need to traverse through all the elements. So there is no chance excluding any other elements, as it doesn't have any right subtrees. So there is nothing to exclude. So we need to traverse through each and every element to check whether the element is there or not. So that's the reason the time complexity of this particular graph is order of n. So the whole takeaway here is we can achieve logarithmic time complexity only for the balanced binary search trees. Now let's move forward and see how what are the different ways in searching for an element in this balanced binary search trees. So tree traversal is something that is the word that we need to understand. So what is tree traversal? The name itself is saying, right? It's a process of visiting each node in the tree. So traversal is nothing but it's traversing through all the nodes in a tree is called as tree traversal. And now we have a binary tree like this. Let's say I have a tree like this. So in how many ways can I traverse through this tree? Can you guess and tell me? So I have a tree like this, and I want to traverse through the trees. And what are the possibilities that we do have?
Traverse through all the left side and then right side.
Mhm.
Other is like traverse through left node, root, and left right node.
Mhm. So basically, let's
Take
yeah, please.
all the left side node and then right side node.
Hmm. So we can do it in two ways. One is we can cover all the elements at the same level is one way. Let's say I'll search, I'll move on to F, and then I'll move on to level 1, and I'll get the values of D and J, and then I'll move on to level 2, and I'll get the values of B, E, G, K, and then I'll get the values of A and C. So one way of traversal is this. So I can start from F, and I can move to D, and I can read J, and then something I'll come back to the next level and I'll read all the values in the same level, and I'll come back and I'll read all the values at the same level. So this is one way, and the other way is, now I have something like this, and I can traverse through all the elements in the left subarray and then root and all the elements in the right subarray. So this continues. It's like a recursive manner. So one is a sequential manner, so traversing through all the elements at an array, and the other one is it's a recursive manner. Now I'll try to read all the elements in the left array and then root and the right array, and if I come back to the left array again, it's something like this. So this is the root, and I'll try to read all the elements in the left array and then root and then right subarray, and again if you go recursively to the last, so again it's something like a and then root and then c. It can be any order, like now we are reading a and then coming to root and then coming to the right subarray, and it can be there will be three possibilities like right, root and left. And sorry, so let's talk about this later. So the first kind is, there are two types of traversal. One is breadth first and the other one is depth first. So breadth first is nothing but traversing through all the elements at the same level is called as breadth first, and the depth first is traversing or covering the left subtree and then root and then right subtree. I mean combining or dividing the right subtrees and left subtrees and the root and traversing is called as depth first search. We are covering the depth first and then we are coming back. So in breadth first search, covering all the elements at the same level is called as breadth first search. So let's talk about breadth first search now. So breadth first search. So breadth first search is nothing but traversing through the elements at the same level at the same time. So this is our tree, and can you say me the order of the elements that in this in the breadth first traversal?
F, DJ,
So F,
BECK, and AC.
yes. So we need to cover all the elements at the same level. So in the first level the value is F, and in the next level it is D and J, right? The next level it is D and J, and in the next level at level 2 we have B, E, G and K, and at the last level we have A and C. So this is how we will traverse through elements in a breadth first search. So we will traverse through the elements at the same level in breadth first search. Again in the depth first search, as I told you, we need to cover all the elements at the elements in the depth first. So we need to cover all the elements in the subtrees, and then we need to move forward to the other subtrees. So we will have multiple combinations here. We can read the left subnode and then root and the right subnode, but the basic thing is we always need to complete the traversal of the left tree before going on to the right tree. So this should be fixed. So we cannot traverse or we cannot complete traversal of right before left. So this is something that is set. So the only thing that we can change is root. Root can be fit at the first or at the middle or at the end. So based on the root we can have different possibilities of traversal. So we can fit the root traversal through the root at the first or in the middle or at the end. So but this should be fixed. We always need to traverse through the left subtree first, and then we need to go to the right subtree. We cannot traverse to the right and then we cannot come to the left. So it should be fixed. So only the root can be changed. Root can be read first or read in the middle or read at the last. So based on that we will get three possibilities. So one is root, left and right. If the root is coming in the front, so it will be left, root and right. If the root is coming in the middle, and it will be left, right, and root, if the root is coming at the last. So we have three combinations here, and we also have names for all the three combinations. So this is called as pre-order. So this traversal, this kind of traversal is called as pre-order, and this is called as in order, and this is called as, last one is called as post order. So this is in order and this is post order. So this names names are also saying something like based on the route traversal. So we are considering route at the first, or traversing through the route, or visiting the route at the first, so we are calling it as pre. And if you are reading after left, it is called as in order, and if you are visiting the route at the end, we call it as post order. It is coming at the last. So these are the three possibilities that can be achieved, or that can be traversed, the order that we can traverse in the depth first search. In the depth first search, there are three possible traversals that we can achieve. One is pre-order, the other one is in order, and the last one is the post order. Hope you understand what is breadth first search and what is depth first search, and what are the different kinds of traversals that we do have in the depth first search. Is this clear for everyone?
Yes, sir.
Okay. Now, for the same tree which is over here, can you tell me the pre-order for this tree? Can you tell me the pre-order?
So do we have to start from the F or from B, like from the bottom to top or top to bottom?
No, we need to start like, if we encounter root first, we need to print it. Let me tell you for one value, so it will be easy for you. So we always start from root, right? So this is the root that we do have, and tree will always point to the root will always be stored to recognize the tree. So this is our root. So we encountered the root, right? So root is something. So this is a root. So we encountered it, and as we visited that, we need to print the value of it. So we encountered root and we printed the value of it. Again, we are coming to the left subtree. After root, we need to traverse to the left subtree. So in the left subtree, we encountered a root again, so we need to print it, and then we need to move to the right side. Sorry, we need to traverse to the left side. So to the D, the left is B. Again, we encountered root, so we need to print it. And then in the right, to the left of this root B, what is there? It is A. So we need to cover it. And after covering left, we need to move to the right. So it will be equal to C. So this is the order that we need to
C.
encounter. So whenever you encounter root, print it. And then if there are no more roots, if both the left subtree and right subtrees are null, then we need to go to the left and the right. So F comes first, and then D is the root, and it has left subtree and right subtree. So root is encountered, so print it. So go back to the next level in the left side. So because after root, left should come. So I move to the left. I move to the B, and then I printed the B as B is the root, and then I need to move to the left side, and I encountered A, and I need to print it. And as there are no more left or subtrees to A, I need to print the right of B, so which is C. And what comes next?
Next is E,
Perfect. What comes next?
J,
Yes,
G,
right.
K.
K, right. So this is the pre-order for this particular tree. So hope everyone understood this. It's simple. So whenever you encounter root, you need to print it. After root, you need to give the priority for the left, and then to the right. So this is the traversal of the pre-order. So root D, and then we went to B, then A, and then we came back to C, and then we came back to E, and then we went to Z and Z, and then we came back to K. So this is the pre-order for this particular tree. In a similar way, can you tell me the in order?
A, B, C, D, E, F, G,
Yes, A
J,
comes
K.
first. So in order is we need to go to the left first. So we encountered root, it has left. We encountered root, it has left. We encountered root, it has left. So the last left that we do have is A, and then we need to print the root B, and then we need to print the right C, and then again we need to print the. So we completed this left. So we need to go back to the root. So D is the root, and the left is E, and then we need to print the root again. So root is F, and then we need to come to the right. In the right we have left is something Z. So after Z we have root as J, and then right, which is K. So this is the in order for this particular tree. Is this clear for everyone?
Yes.
Yeah. So can you tell me the post order?
B, A, C, B.
Yes, right, perfect. A, C,
A,
B,
B, E,
right,
D.
right,
Um, I think after that it's G,
right,
J, K, F.
G, K,
G, K, J, F.
yes, right. This is the perfect order. So in post order, we need to cover the left first, and then we need to traverse to the right, and then root. So that's why A, C, B. So we covered the left, and then we need to go to the right. So E comes first, and then D. So we covered the entire left, and then we need to go to the right. In the right we have also left. So Z comes first, and then right K, and then root. And the final root will be the root node, and final element will be the root node. So this is all about pre-order, in-order, and post-order. So now it can be any kind of graphs. You can write the breadth first search order. You can write pre-order, in-order, and post-order for every tree that is given to you. Okay. So now let's see how can we implement these trees. I mean, we'll look at the frameworks of these orders, these traversal orders or these search orders. So let me take a new slide. Let's say I have, let me take the same graph again. If say A, B, let me take C, D. So this is the graph I am given. A, C. So as we are discussing earlier, how do we store these elements basically? So in a tree, every node will be saved like this. So it's again like a memory block which will have basically three values. one is the data or the key. So basically one will have the data f, and to the right, the left side, it will store the reference of the left subtree or the next left root. So let's say it will store the value of the reference of the a, and to the right it will store the reference of the right subtree. Let me take it as, so let's take the addresses or the references of everything. So 200, 100, 300, 500, 600, 700, for f it is 800, for e it is 900. Let's say these are the references for all the nodes in the tree. So along with f, it stores 200 here and it stores 100 here, which points to the left subtree and the right subtree. Okay, in the similar manner for a, it will have three blocks. One is value to store a and the other one is 3 and 700. So if you consider c, it will be 500, c 600. If you consider z, it will be null, z and null, as it doesn't have any uh, left subtrees and right subtrees. So this will look something like this. So for the leaf nodes, we will not have any left subtrees and right subtrees. So here the value will be is equal to null, and to the right it will be is equal to null. Now I want to traverse through the elements at the same level at once. So how do we do that? How can we achieve that? Basically, can you think the way how can we implement this? Any ideas? Okay, so basically we can achieve this with we can achieve breadth first search with queues. So let's see how can we do that. Let's say I have something like this. So initially I'll start with root. Okay, so the traversal will be something like this. So initially I'll start with root, and then I'll also take the references because root is the starting point for traversing any kind of trees. So from root we will start traversing to the left or the right. So root is something that tells us to recognize the base. To root is something that tells us to recognize the root node. So now we will reach out to the root node, and after the root node we will fetch both the left and the we will fetch both the left subtree reference and the right subtree reference. So in the queue after 400, which is the start node, we will get the references of the left and right. So the references of the left and right is 200 and the 100. So 200 and the 100 is comes next. After 200, so we now we know 200. So after 200, once we are visiting 200, we will take the left and right of it. So what are the left and right of it? It is 300 and 700, that we are gonna print 300 comma 700 is, or the next values that will come. So now where we are at address 200. So we printed, so you see we went to 400 and we took both the values of the left reference and the right reference, and we printed we added them to the queue. So for 400, left and right are 200 and the 100. Now we will come to the next item in the queue. So it is 200. So in 200, once reaching 200 address, we are taking the left and the right values, right references of that particular node. So the left and right references are 300 and 700. We are adding them to the queue. Okay, so we added 300 and 700 to the queue, and now we will move on to the next item in the queue, which is 100. So we will reach to this reference node, which is 100, and once we reach it 100, we will take both the values, both the right and left references of them. So right and left references are 800 comma 900. Okay, so we added both the items to the queue, and then the next item in the queue is 300. So we reached here, so we will add the left subtree and the right subtree values to the queue. So left and right will be 500 comma 600, right? So I'm adding them to the queue, 500 comma 600. So next, what is there? 700 is there. For 700, left and in the left and right we don't have anything, so we doesn't need to add anything. So both have null, so we doesn't need to add them. And then we are moving to 800, it doesn't have anything. We are moving to the 900, it doesn't have anything, so we don't have anything to add now. So everyone understood this, how we are adding items to the queue or the references to the queue?
Yes.
Anyone wants me to repeat this? Okay, so I'm just doing a quick recap. So we are starting with root, and at every node we are adding the left reference and the right reference to the queue. So that's all we are doing. So we are starting with 400, which is the base node or the root node. For the root node, the references are 200 and the 100. So the next item in the queue is 200. We should add the references of its right and left to the queue. So its right and left references are 300 and 700. We added them to the queue, and then we move to the next item in the queue, which is 100. So for 100, left and right are 800 and 900. We are adding them to the queue, and then we move to 300, and we are adding the right and left of that particular uh, element in the queue. So for 700, 800, what are those? 700, 800, and 900. We don't have anything. These are all leaf nodes, and 500 and 600 are also leaf nodes. So we don't have any left and right references for them. So this is how we need to add the elements to a queue. Now let's print the values in this. So what is the key at 400, at address 400? It is F, right? So at 200 it is A, and at 100 it is B, and at 300 it is C, and 700 it is D, and 800 it is F, and 900 it is E, 500 it is G, and 600 it is H. So is this not the breadth first order? So F, after that A, B, and then we went to C, D, F and E, and then we came back to Z and H. So this is what we need to achieve in breadth first search, right?
Yes.
Yeah. So this is how we are gonna achieve the traversal in breadth first search. So hope everyone got this, and I'm moving forward to the depth first search now. So again, in depth first search, what are all the orders that we do have?
Pre-order, in-order, and post-order.
Yes. So let's quickly discuss each and every orders and their implementation frameworks. So let's take a pre-order. So again, let me take a small tree. A, B, C. So this is a tree I do have. Inside this I'm writing this. Okay, so I'll call this as the pre-order logic. So is this a recursive function?
Yes.
Okay. So now let's debug this and see how what we will get the output. So now we are starting with the pre-order function, and in the main we will pass the root. So we will call this pre-order, and then root is, what is the root in our case?
F400.
Yeah, 400 is the root address. So that comes here. So it is checking root is null or not. It's not null. So then it will print the data at the root. So what is the data at the root? It is F, right? So for this I'll call this as, we are at 400, address 400, and then what is that? Pre-order left address of that. So root left is 200, right? Correct. So this is our root. Root's left is 200 and right is 100. So after root we printed the data in the root, and then it's a recursive call, and the recursive call is pre-order root left. So root left is 200, so we are passing 200 now. So what will be the function call now? It is pre-order 200 is the call. So we still have, in at this particular level we have pending this pre-order root, right, is still pending. But as we reach the recursive call, so we are going on to top, we are checking whether it is right or not. So root is not null, so we are printing the data at the root. So what is the root now? Root is d, right? So we are printing the value d. So again we printed the value, we are coming back now. So again it is saying pre-order root left. So what is the left of this root now? 600 is the left, right? So again it's a recursive call, and you just need to notice this pre-order root left is pending for this as well. So for both f and d it is pending. So right is pending for this, right is pending for this. So as we are in a recursive calls, we are just executing the same thing again and again. So after d we are again reached to this point. Here root left is 600, so root now will be 600. We are checking, so let me write that as well. So now what is the root? So now we reach pre-order 600, right? So that is root, and we now we need to print the value at the root, which is b. So I need to print b here. So after b, after printing b, again I need to go for root left. So root left is 700, so my order will be pre-order 700 is my next recursive call. At 700, now root will be 700, at root is not equal to null. And so what will the data? We need to print the data at that place. So it will be z, and then again it comes here. So root left, so what will be the left of this particular root? 700. It is null. So if I am coming to null, it is written. So here I'm returning, so it pops out from the stack, so it goes here. So 600, so after printing, so 600 stop here, and then the next statement is pre-order root right. So what is the right of this 600? It is 800, right? So the reference goes to 800 now. 800 is not equal to null. We need to print the data at 800. So next goes to pre-order 800. Pre-order 800 is the next. So what is the data at that 800? It is h. It will be printed, and then what is the next statement? So with this we completed the function at this 700. At this, so at this 600 we completed it, so we need to go back to 200. At 200 we need to execute this root right. So root right will be pre-order 900, right? Hope everyone is getting this right. It's just a recursive call, and we already discussed this. 900, the value is c. It keeps on continuous, like we completed this now. So for f we have something, this root right is pending. So we will come here again, we'll print this root and we'll check for the left. So left is 150. This will be called recursively. So after 150 it will check for null, it will check for the left is null, so it will be popped out from the stack, and then it reaches to left, and it will execute that right left, which will be the last statement for this particular stack root. Did everyone got this? So this is a recursive call, and this is a simple function for achieving that. So in the recursive call, we are going to the left root, we are printing the root data, we are going to the left, we are keep on checking whether left is right or not, left is there or not. Left should not be null. Until then we are traversing through all the left nodes. After completing all the left, we are coming to the right for each left. So for each left we are coming to the right. So after for each left we are coming to the right, again we are checking the left, and we are printing root, we are checking left, we are going to as depth as possible in the left until unless it is equal to null. So after completing left for each iteration, we are coming to the right of that iteration, so we are printing the right next. So this is how pre-order will be achieved. Everyone got this?
Yes.
Okay, so this is just a recursive, and you can put it on paper, and you can again debug that with clear addresses, and where it is left, where the stack is pending, and after completing, after popping from the stack to which it will go, and all this stuff you can clearly analyze that. But only thing that you need to have handy is this one. It's very simple. It's like two recursive calls to the left and right, and printing the root, and just have that pre-order function and call it recursively for both left and right. Okay, so that's all about pre-order. The other orders that we do have is in order and post order. Let's have a look at that quickly. Give me a second please. Okay, so uh, this is the post order, and now let's quickly see the in order. So what is the difference between pre-order and in order?
In order, root comes in the middle.
Right, that's all. So this is how in order can be achieved. If you look at this, until unless root is null, it will keep on doing this in order function. So this will not be inside this loop. So this part will be outside the loop. So inside if loop, only return will be there, as we discussed earlier. This will be outside the loop. So this is and the outside the if loop. So if you see, in order will keep on executing this root left. So if you consider this root, this is the root dot left is not null. So it will keep on calling it recursively root until root is equal to null. There it will exit out from this particular function. So root dot left, it traversed here, and then root dot left is 600, and again root dot left is 700. So here it will be null, root will be equal to null, as because root hyphen left will be is null here. So after, so here it will pop out this, and it will come here, it will print z, which is the data, and then it goes to the right of it in order root right. So there is no right, so it will again come back to 600. So it comes to 600 for the previous one. If you analyze this, so it came from here to here, here to here, here to here. Here it popped out that from the stack frame. So it printed the data, and then it goes to the right is null, and then again it comes here. So what is a root? It's root, right? So it is pending for one of the left. So it prints the data, and it goes to the right, and again it comes to this, prints the data, goes to the right. So it's just the order. Instead of printing the data first, it's going to the left, as much left as possible, and then it is coming to the root back and going to the right. Understood? So this will goes on recursively until it reaches the last point in that particular tree, because it needs to have root is equal to null to stop this recursive calls. Until root is not equal to null, it will not stop, and it will not go printing the data. That is what we need to achieve in the in order. We need to go to the most left node, and then we need to print the data of that, and then we need to come back to the root, and then we need to print the right. Correct? So will this achieve that? Any questions in this, or do you want any clarifications in this recursive calls? Is this sufficient to achieve the in order? Is this lines of code? Uh, Can you tell me if everyone understood this or not? Like, if not, I'll try to explain uh, by putting all the things in the stack in order, and then I'll try to explain it. If not, we can move forward and we can look it into the other orders.
Pick one.
Sorry. Everyone got this?
Yes.
Yes.
Yeah. So it's the leftover is post order. The post order is same. It comes first it comes left and then right and then print. So again it's similar to this. So we need to create a class or method like post order. In the post order, we need to call something like this post order. It should be left first, and then it should be post order right, and then it's like print data. So in post order it comes left, right, and then data. So this is all how do we achieve breadth first search and depth first search, and also different orders implementation uh, in depth first search, pre-order, in order, and the post order. So this is pretty much about traversals or searching an element. So searching an element is nothing but as we are able to traverse through all the elements, so we can match it, right? Like uh, we doesn't necessarily need to traverse, we need to put a conditions in this traversal. So if you know the whole traversal, we can traversal through half of it. So the only thing is like you need to put some condition, like if value is less than key or value is greater than key, or something like that. We just need to put some if conditions, and then we need to restrict the other subtrees. So this is all about traversals and searching a node. And now coming back to the binary search trees, let me say something. Now we will look at deleting a node, deleting a value in the binary search tree. So I want to delete a particular node in a binary search tree. So what are the cases? Let's understand what are the different cases that will be there. Deleting a node in binary search tree. So if I want to delete a node, if I want to delete some value in this particular binary search tree, so let's see how do I do that. So as I told you, for every node that we have this basic structure. One is the data, and the other one is left and the right reference values for that particular node, or the left and right subtree references for that particular node. Let's say for A, I have the data A, and to the left I will store 150, and to the right I will store 250. Now, if I want to delete this F from this binary tree, so if I want to delete F from this binary search tree, what should I do? I just need to unlink this, right? So I just need to unlink F from this A, so that F will not have any references. So this will be allowed for garbage collection. So the garbage collector automatically releases the space that is allocated for this node. So the only thing that we need to do is we need to untag the reference of this f in this a. So this a has this f reference. So if you are able to untag this reference from this a node, so this is a free space that is there, and garbage collector will take care of this. It will remove, or it will deallocate the space that is allocated for this f. So for that, what all we need to do is, so basically for f we have something like this. So the data will be stored here, which is a, and to the left it stores the left reference, and to the right it stores the right reference. So okay, so the right reference is 250. Now our condition here is we need to remove this f or untag this f. So to do that, what I need to do, instead of this 250 storing 250 reference, the f's reference to the right of it, I just need to make it as null, right? I just need to make it as null, so that it's a consideration saying that for a we don't have any right subtrees. It has only one left subtree, and the address of that left subtree is 150. So this says that it doesn't have any left subtrees, and f will not have any references stored. So when once we don't have any references, it will be allowed for garbage collection. So this will be this will be cleared by the garbage collector, and we will have only this tree that is left with us. So is this like deleting a node from a binary search tree?
Yes.
Yeah. So let's say if I want to remove e, what should I do?
Remove the link between A and E. You can put A left side as null.
So this comes as null, and it will be 250 now. So there is no problem in that case. Like, we just need to keep the left subtree as null, so that references to e will be lost. Okay, now let's consider another case. So this is for all the leaf nodes. Okay, this is valid only for the leaf nodes. Let's consider this for leaf nodes. Let's we will discuss some other cases, so that you'll understand why this is applicable only for the root nodes. Let me remove this. So as I said, this case is for the leaf node. So we just need to change the references to delete a node. In this case, if I want to delete a, my criteria here is I want to delete a. What should I do? Node has one child. So can I do this? So delete a, can I tag e directly to the f, so that e will not be lost? If I make the left reference of f as null, so I want to delete a. So if you think like doing this way will delete a, means it will not work out. Like for f we will have three blocks again. One is the data, and the other one is left reference and the right reference. So this is the right reference for the a. Here in this particular root node, it will store the value of 100 as the right reference. So here the 100 will be there. If I make this as null, it will remove a's reference from this, and so it not only removes a, it will remove the entire right subtree. So which is not desired. We doesn't want to remove the entire right subtree. Instead we just want to remove only a from the tree. So in that case, can I tag e directly to the f? Can I tag f directly to e? Can I tag f directly to e? I mean, instead of null, can I store 150 in this?
In this case, yes.
Yes, in this case it is yes. So in this case, in the sense any node has only one child, we can tag the child node to the parent node. So it can be right subtree or the left subtree. Even if it has f, we can tag that directly to the let's say it has some other child called as z, and it has only right subtree, it doesn't have left subtree, we can directly tag it to the parent node. In the similar manner, I mean grandparent. So here it is E, it has only one child node, and I want to delete E. So I want to delete A so that I can directly tag the child node to the grandparent node. So I can tag E to the F. If it has only one right tree, we can tag that directly to the grandparent node if we want to delete the parent. So this applies for all the nodes which has only one child. Am I correct? Or
Yes. With
yes.
only one child, you can do that.
If it has only one child node, we can tag that node directly to the parent node, because we don't have any other possibilities that will disturb us. Like, so if it has another child, then we need to think of the cases. So if it has, let's go to that case. So if you have only one child, tag it to the parent node is the solution to delete that particular node. So what we need to do here is tag it to the parent node, tag to grandparent. Now the other case is, what is the other case? We if node has two childs, there is only three possibilities. One is zero nodes, one is one node, and the other one is two nodes. So because in a binary tree, the maximum number of nodes, a node maximum number of subnodes or the children that a node can have is two. So we will left with only one case, that is node has let's put this in different color. Node has two children. Node has two children. So let's take an example here. Let's take f. If I want to delete f, what should I do? Now the requirement is I need to delete f. So this f has to be deleted. So if I need to delete f according to the binary search tree criteria, so all the values that are to the left of this has to be lesser values than the root, and all the values to the right has to be more than the root node. That is the basic criteria that should be achieved, or the prerequisite that needs to be achieved. To do that, if I want to delete this f, or if I want to delete the root node, I should keep a value here so that the tree should not get disturbed. So a value, in the sense, what should be the value? I need to fetch the maximum value from this left subtree, or the minimum value from this left subtree, and I need to fit it here. Either of the ways I has to do it. Either I need to pick the maximum value from the left subtree, because after root node, the next value that will be in middle is the maximum value in the left subtree, because left subtree should have minimum values than the root node. All the values in the left subtree should have lesser values than the root node. So if I'm deleting the root node, and all the values to the left subtree should have lesser than the root node, means it should be the maximum value in the root node, right? What is the maximum value in this root node? Let's say 900 is the maximum value. If I place 900 here, so it will satisfy this. So this is not a binary search tree. No, these are the references, right? So these are the references, so these are not the values. So let me keep some values here so that you'll able to understand it clearly. So let's say I have 12, 5, 4, 9. Here I have 15 and 22. So this is the tree I have, and I want to delete 12 now. So I want to delete 12. Even if I delete the 12, my basic condition is the tree should not be disturbed. So to do that, to keep the binary search tree condition achieved, can we take 9 or the maximum value from the left subtree and can we place it here? Let's say let's pick some other value, let's pick 5 here. If I place 5 here, what happens? So the basic criteria or the prerequisite for the binary search tree is not achieved. Why? Because the left should not have any more values than the root node. So now I'm deleting 12, I'm making 5 as my root node. So I have 9 which is greater than 5 on the left subtree. So it is not a desired case for the binary search tree. So this can be achieved only if I place 9 here or the maximum value in the left subtree. So if I place 9 here or the maximum value in the left subtree, what happens? So I tag 9 here. So all the values to the left of this 9 will be less than this because we picked the maximum value from the left subtree. So maximum value from the left subtree is nothing but all other values in the left subtree is lesser than the maximum value for sure, right? So the maximum value is 9. So all the values to the right will be more than this because we pick the maximum value from the left subtree, and so any value in the right subtree will be more than any value in the all the values, like any value in the left subtree values, uh, in the left subtree values, because we pick the maximum value. So we know left subtree will have the maximum values and the right subtree. So we pick the maximum value because we need to make sure that all the values in the left subtree should be more than the value that is placed in the root node. So I should not place any other values other than the maximum value in the left subtree to keep the binary search tree safe, or to keep the basic criteria of the binary search tree is left, or else I have another way. I can also keep the minimum value in the left subtree. I mean in the right subtree. In the right subtree, I can pick the minimum value. Still, even if I pick the minimum value, I can play. If I pick the minimum value and if I place it here, let's say the minimum value in the right subtree is 15, and if I place the 15 here, the tree structure will be maintained safely. Because if I place 22 here, if I pick 22 and place it in the root, what happens? 15 is less than 22, so that binary search tree is disturbed. So if I pick the minimum value from the right subtree, then the structure will be maintained. So there are two ways. One is to pick the minimum value from the left subtree. We need to pick the minimum value from the right subtree, or else the maximum the maximum value in the left subtree or the minimum value in the right subtree. Max value in left subtree, or we need to pick minimum value in the right subtree or minimum value in the right subtree, and we need to replace that in the root node. So what is that? Then we need to replace that in the root node. Replace in root node. Accordingly adjust the delete node references. So we are just moving the 9 to the root node. Now we also need to remove the references of this 9 to the 5, right? So reference of 9 to the 5 has to be removed as we are moving this 9 node to the root node. So these are all the steps that needs to be followed when we are deleting a node with two children. So the whole criteria here is like we need to pick the maximum value from the left subtree or the minimum value in the right subtree. Then in these two conditions the tree will not be disturbed. So it's a simple logic, and then we need to move make the replacements accordingly. So as we are removing one of the nodes in the trees, we need to adjust the references accordingly. So these are the three cases that we will have while we are deleting a node in the binary search tree. Hope everyone got this right. Is this clear for everyone?
Yes.
Okay, so I have something like this with me. So I have my code. You will get code for everything. So this is my binary search tree code, and it has everything: implementation, it has insertion, that it has deletion. We have a deletion code as well ready with us. So you can, it's just a simple Java, and you can start debugging this. Let me explain you this delete code alone. Like I'll try to debug this code alone. So the rest you can do the analysis. It's a simple Java analysis. So put it on paper and you'll get the logic for that. So let me explain you this delete thing. This is the code that we do have. Let us take the tree as well. This is the tree. So this is the tree, and the calls is so I'm putting this link in the chat so you can take it as reference to get this binary search tree code. So what are the deletions that we are doing? So we are deleting three cases. So 45, control C, and paste it here, control V. So this is the main method call. So we want to delete some keys from the main method. So 12 is a leaf node, 90 is the node with only single child, and 45 is the node with two child. So let's debug this, understand how the function flow goes. Delete. So we have three calls. One is to delete 12, and the other one is delete to 90, and the other one is delete to 45. Let's start this. So it called a method called as delete key, and the key value is 12 here. Okay, so the key value is 12 here. Initially the key value is 12, and now inside this, again the root is a global variable which stores the current reference that is there. So root is something that will store the references of the current node on which we are. So initially the root value will be the value of this 45, right? So this is the root that we do have, So 45's reference will be stored here and the key value is 12. Now it called this function and the node's reference is something like this and the key is 12. So root in this case is, what is the root in this case? It is 45's reference. Now we are coming down, we are checking if root is null or not. Root is not null, and here we are checking key is less than root dot key. What is root dot key? Root is the reference of 45. Root dot key is nothing but 45, right? So root dot key is 45 and key is 12. 12 is less than 45. Is that true? So 12 is less than 45. It is true. So we need to go into this particular if statement. In this if statement, it is given like root dot left. Again, it called this function recursively, and now this root value will be changed to root dot left in the next round of regression. So so now we are calling this function recursively here. So now we are calling this function recursively. This goes back to this. So this call will goes to here, and now the root will be is equal to, what is the root now? Root is 10th reference. Root is 10th reference and the key is 12. Key didn't change. Now we came here to the 10th reference and we are moving down. So root is equal to null is not true, and now 12 is the root, 12 is the key, and the root is 10th reference because we passed root dot left. So root dot left will have the reference to the left subtree. So this is the root earlier, which is marked in red color, and this left is nothing but 10th reference. So that's why we got the 10 reference here. Now it came down, and here the validation is the key is 12 and the root dot key is 10 because the root now pointed to the 10th reference. 12 less than 10 is true or false. It is 12 less than 10 is false, so it comes down to this statement now. So here we are again calling it recursively. What is the recursive call that we are doing? So here we are passing root dot right instead of root dot left. So if it is lesser, we are passing root dot left because all the left elements will have lesser values, and if it is right, we are passing the right reference. Now the function call goes from here to back. It's a recursive call and it goes back to here. So now here the value will be, now what is this? Now it will be 12 reference because we passed the reference of right, and the key is again 12. So we have done that. So call goes to here 12 reference and 12. So again it comes down, root is not equal to null because it's pointed to 12 reference. So 12 is, now key is 12 and root dot key is 12. So 12 less than 12 is false, and it goes here. 12 greater than 12 is false. Now it comes down. Now it comes down. It will check if root dot left is null or not. So what is the root now? 12 is the root. 12 dot left is null, right? It doesn't have any left subtree, so it is null. Now it is calling return. Return root dot right. What is the root dot right? Root dot right is null for this 12. So that root dot right will be assigned back to root dot right of this. From here, this is the recursive call that we have done, and it is coming down. So now this recursive calls return value is null. So root dot right will be assigned to this root dot null, and which is nothing but this value. So the null will be assigned to 10 now because it's the 10th check. So 10 will be null will be assigned to this 10. So root dot right. So this is the root in the previous stack call, and that root dot right will be assigned with null by removing the reference to this 12. With thus it is end. So this is an if. We went into this if in this else, and it's written. So the function call will be ending. So it comes back to the last reference call, and it will just return, nothing will be satisfied, and it will return the value. Hope you understand this, right? Did you got this, or do you want me to explain this again? Hello.
Yes, sir, got it.
Yeah, so I don't think like it's not an easy thing to understand at the first time, but you try to get the code from the link and put it on paper and try to debug it. Recursive calls are different, are difficult to get them for the first time, but you just try to do them. So you just try to this one was- so you just try to put the values this way, and then you'll come to know. So mark at every instance, you just try to mark whether the value is pending here or not. If there is any pending stack calls that are there, so you just mark it as pending. So you just try to mark them as pending so that it will be clear for you to debug them. So that's pretty much. So for everything it is same. So if you are deleting a key of 90, so as I explained you, this 50 will be tagged to this. So if it is a delete key, we need to fetch the minimum value from root dot right or the maximum value from the root dot left. So that will be achieved at this point. So this minimum value is something, is a function which will return us the minimum value from the right subtree. So that is assigned to the key value of the root. So this is the root, and for that key value we are getting the minimum value and we are assigning it. So with that, and then we are recursively deleting it. So we are deleting that node in this particular function call. So we are getting the minimum value and we are deleting that function call, and we are assigning that minimum value to the key value. So this is how to debug this binary tree, and you have the entire code here. If you didn't get something, you can ask me in the next session. But when you debug it perfectly and you mark the pending stacks, the values of the root at every instance, it will be easy for you to understand. And you have all the code available for here, for insertion, for searching, and for deletion. You have all the code readily available here, and it's a static code. There is nothing to change. So you can just try to debug this in the Eclipse, or it's very good to put it on a paper and trying to debug it. Hope you can do it on your own, because you're very good with something like in Java you're comfortable, right? So it will be easy for you to debug this. So it's nothing, but the only difficult part here is like to track the recursive calls. If you're able to track the recursive calls perfectly, it's easy for you to understand. There is nothing much Java here. Only the important thing that needs to be tracked down is recursive calls and the values of the reference variables at that recursive calls, and the pending recursive calls at each and every function calls. So that's all you need to understand when you're debugging this. Hope you can do this on your own. So I'm leaving it here, and if you have any queries, you can do it in the you can ask me in the next session. And if you're good at understanding this, it's pretty good. So that is pretty much about breadth first search, depth first search, and implementing a binary search tree and searching in a binary search tree. You have a code readily available for binary search trees as well. So it is node search recursive. So if you see this, if the key is greater than the given key, we are just returning, we are we are only taking the left part of it and we are doing it. So we are not considering right part for the search, so that we are reducing n by 2 times of we are reducing n by 2 elements from the search list. So we are considering only n by 2 elements. Or else if the key is greater, we are considering only root dot right instead of root dot left. So again we are excluding n by 2 elements from the search list. So this is how we will achieve logarithmic of n in everything, in deletion, in search, insertion, and deletion. So if you go to any of the code, you will see that in the delete, again you'll see recursive root dot left or root dot right. We are considering only half part of the tree. Even in the insertion, if you see the insertion code, you'll insert the values in the similar order. So you'll keep on checking for the left values. You will keep on checking for the nodes where it exactly fits. I mean, if you're inserting something, it should go under that particular node, right? So if you want to insert something, it need to keep on it needs to go to the particular. If it is less than the root, it goes to the left. Again it will check. If it is less than it, goes to the right. If it is less than it, it goes to the right, and it will fit somewhere in the right side. So again in the insertion, it will every time what to say, every time it is excluding n by 2 elements. That's the reason for binary search tree. For insertion, deletion, and searching, only we can achieve logarithmic of n time complexities. So if you go through this code, you can easily see that for everything, for insertion, deletion, and searching, you'll see an if condition and else condition, where in if you'll see root dot left, and in the right you'll see root dot right. So that's the way we will achieve logarithmic time constant in binary search trees. So that is pretty much about binary search trees and its implementations. Is everyone clear with this? The only thing that you need to do is you just need to try to debug this, and you need to keep a track on the recursive calls perfectly, so that it's easy for you to understand. Is it clear? Can we move to the next topic?
Yes, sir.
Okay. Now let's move on to the other kind of data structure called as graphs. So what kind of data structures array list, linked list, vector, stack are? Are they linear or non-linear data structures?
Linear.
So what about tree?
Tree is not linear. Non-linear.
Non-linear data structure. So graph is also a non-linear data structure. So graph basically looks like this. So if we come to the definition of a graph, graph is an ordered pair of set of vertices and set of edges. So what are vertices and edges here are? So these are the vertices. So these are the vertices that we do have. Graph is a set of ordered pair of vertices and edges. So let's understand what are vertices and edges. I call these circular dots as vertices, and these lines joining the vertices are called as edges. So let's name them. So these are the vertices. So let's say v1, v2, v3, v4, and v5. These are the vertices that we do have. And edges, what are the edges? So this is edge, right? v1 and v2. So let's call this as edge 1. So these are the edges. Let's name them e1, e2, e3, e4, e5, and e6. These are the edges that we do have in a graph. So graph is an ordered pair of, so the definition of the graph is ordered pair of vertex and edges. Now what is an ordered pair? Anyone know what is an ordered pair? So we call a pair as an ordered pair if, say, a pair like this is the representation of a pair. A comma B should not be equal to B comma A unless A is equal to B. So this is called as, if you consider a values, this is called as ordered pair. So let's say this edge, like if you are able to traverse from V4 to V1, and we should not be able to traverse back from V1 to V4. So those kind of things are called as ordered pairs. So this is called as an ordered pair. A comma B should not be equal to B comma A unless until A is equal to B. So this is called as ordered pair. So a pair is called as unordered pair, and unordered pair will be represented with flower braces, and unordered pair is something like A comma B is equal to B comma A. When A comma B is equal to B comma A, we call this as an unordered pair. This is unordered pair, and this is ordered pair. This is ordered pair. Okay, so this is the two things that defines ordered pair and ordered pair. Now you got the definition. A graph is an ordered pair, so that if A comma B should not be equal to B comma A of vertices and edges. So as I said, graph is an ordered pair. So ordered pair will be represented with braces like this, and it's an vertices comma edges. So it is an ordered pair of vertices comma edges. So this is all about, this is the definition of a graph. So if you want to represent set of vertices of a graph, we can do this way. So we can be represented as set of edges. Like if you want to represent set of vertices, you can represent this way. So open and flower brace, we have 5 vertices, v1 comma v2 comma v3 comma, so on. This is how to represent a set of vertices. Now how to represent a set of edges? So even now we want to represent edges. So edges can be represented this way. So edge 1 is something that is traversing from vertices 1 to vertices 2, right? So it's going from v1 to v2. Okay, and e2 is moving from v2 to v3, v2 comma v3. So similar way, edge 3, e3 comma v3 comma v5. This is how we'll represent a set of vertices, I mean set of edges. So it keeps on going. So this is the way to represent vertices and edges of a graph. So this is a simple definition. Edge graph is a nonlinear data structure, and it's an ordered pair of vertices and edges, and a set of vertices can be represented this way, and set of edges can be represented this way. Okay, that's all about graph and its definition. And now look at different types of graphs that we do have. So now let's see different types of graphs. So the first type of graph is uh, directed or undirected graphs. So directed graphs or undirected graphs. So what is directed graph and what is undirected graph? Let's take this way. For example, I have something like this. So if I mark the edges this way, so this way I'm representing it. So we have some ways. For example, uh, so let's understand what is directed and undirected graph, and then we will move on to the examples. So this is the graph that I have, and it is directed. So we can move from v4 to v1, but we don't have any path from v1 to v4. So we cannot move back from v1 to v4 because there is only path that is existing from v4 to v1. This is directed this way. So anything of the edges is, if the edges are directed, we can call that as directed graph. If the edges are not directed, if you see the earlier case, if you remove these things, let me put that as well so that you'll get a clear understanding of it. So this is some of the graph, screen graph that we do have. I'm joining them. So this is an example of undirected graph. So there is no directions that are given from one vertices to another vertices. We can move this way or we can move this way. From v4 to v1 or v1 to v4, we can move both the ways. Whereas in directed graphs, we don't have that feasibility. We can move only in one direction. From v4 to v1, we can move, but we cannot move back from v1 to v4. So that's the whole understanding, that's the whole difference between directed graph and undirected graph. Now can you tell me any examples for these graphs? In what case in the real world we'll see directed graphs, and in what case we will not see the directed graphs? So if you take an example like this, like let's say in our cities we will have one ways, right? If we cannot move in both the ways. So if you are in Google Maps, wherever we have one ways, we just need to represent that with directed graphs. Says that we can move only in one direction. We cannot put both the ways. I mean, we cannot allow a vehicle to pass from v4 to v1 and v1 to v4, right? If it is a single way. So in that cases, we need to represent those kind of nodes or the graphs as directed graphs. So if you take another example of Facebook, let's say uh, he is a person who has and these three v1, v3 and v4 are in friends list of v1. So he can send a message to this guy, and this guy should also have a feasibility to connect this with this guy. So it should be an bidirectional graphs. So they has to be mapped bidirectionally. So whatever actions that he can perform on this person has should have the same feasibility to perform the same on this person as well. So in that case, the relation between the nodes has to be bidirectional. So it should not be a unidirectional way. So you can take that as an example for bidirectional or undirected graphs. You should not be anything that directs us. Whereas in directed graph, you should have a specific direction. So from what vertices to what vertices, you need to perform the operations that needs to be specifically given. So to simply define, to wherever it is, wherever we define the direction, it's called as directed graph. Whereas it is not defined, it is called as undirected graph. Okay, now let's take this is one kind of differentiating a graph. The other kind is weighted and unweighted graphs. Weighted graphs or unweighted graphs. These are another type of defining a graphs. Let's say I need to move from one place to another place, and that should have a definite amount of distance, right? Let's say 100 kilometers. Without defining this, there is no point, there is no meaning for this particular graph, right? So we need to, if we are considering some graphs, we need it's need to weight them. Let's say weight in the sense, let's take this as a Google map. If we want to move from destination v4, like starting v4 to destination v1, we need to move from this source to destination, and we need to tell to the user what is the weight of this edge, or what is the amount of distance that you need to cover. Without specifying this, there is no point defining or connecting this nodes using this particular graph. So wherever we define the weight of it, we call that as weighted graph, and if the weight of all the nodes is similar, we call that as unweighted graph. So if the weight of all the edges is equal, which is equal to one unit, or let's say it's a common unit, we call that as unweighted graphs. If the edges has some weight that is defined on them, we call them as weighted graphs. So it's a simple example. Whenever we are going on some, you can take it a Google Maps. In Google Maps, from destination node to your source node, it should specify as the distance. Without that, there is no meaning for the graph. It cannot just connect the points, it also has to say the distance. So those kind of graphs are called as weighted graphs, and wherever the weight of all the edges is equal or equal to unit 1, we call that as unweighted graphs. Okay, right. And the another type is strongly connected graphs. Connected or unconnected graph. So a graph is said to be connected if we can traverse from any node to any another node. We can call that kind of graphs as connected graphs. And if you are not able to move from one vertices to another vertices, we call that as unconnected graphs. Let's take an example for both connected and unconnected graphs. So let me take another example. So let's take the differences between an example for connected and unconnected graphs. So I have something like this. This is one graph that I do have, and the another graph that I have is, take two graphs here. You connect all of them. This graph with this graph, this this let's mark them. This one. So can you tell me what is connected graph and what is not connected graph here? So the basic definition is, for connected graph, we should be able to traverse from one node to any other node. We should be able to traverse from one node to any other node in the graph. So this is the definition of a connected graph and unconnected graph. So here we have four nodes. We can traverse from any node to any other node, right? This is undirected graph. So there is no restriction on traversing. So we can move from this node to this node. We can move from this node to this node. So we can move from any one node to any other node. So this is called as connected graph. Whereas it is not possible in this case. So from this node to this node, there is a way. But from this node to this node, there is no way. We cannot move from this node to this node. Like, let me call this as A, B, and C. So let me call this as A, B, and C. So we cannot move from C to B. We cannot direct from C to B. So we don't have any path for going from node C to node B. So we call these kind of graphs as unconnected graphs, whereas these graphs are called as connected graphs. So you got all these differences. What is the difference between directed and undirected? What is the difference between connected and unconnected graphs? And what is the other? Weighted versus unweighted graphs. So directed, undirected, weighted, unweighted, and connected and unconnected graphs. Everyone got this? Three differences.
Yes, sir.
Okay. So there is something called as self-edge in graphs. Self-edge is nothing but edge has to be start. The name itself is saying, right, self-edge. It means like the edge has to start at the same node and should end at the same node. So how do I write? So if there is an edge which starts at the same node and ends at the same node, we call that as self edge. Okay, so this is an example of the self edge. It is starting at the node A and it is ending at the node A. So we call this as self edge. So there is something called as parallel edge. I means it means like, so there should be two pathways. Like this is from A to B, and there is also another way from A to B. So these are called as parallel edges. So these are called as parallel edges. So these are called as parallel edges. Uh, the best example for this is like, if two flights are traveling from source to destination, there should be different pathways or the different edges for both the flights that are traveling this way, right? So in that case, these parallel edges will comes into picture. There can be n number of flights that traveling from the source to destination. So for every flight there should be a separate edge that needs to, or a separate path that needs to be created. So those paths are called as parallel paths or parallel edges. So this is self edge and this is parallel edge. Okay, so let me take another example and tell you something about that. So this is my graph. Can I call this as graph?
No,
Why?
because not connected.
Yeah. So one thing is, you doesn't necessarily need to connect the vertices. So a graph can be have null vertices. Nodes can be disconnected. So here the vertices can be represented as, let's name them as v1, v2, v3, v4. So this is v1, this is v2, and this is v3, and this is v4. As I told you, graph is an ordered pair of vertices and edges. So it should be represented as an ordered pair of vertices and edges. Here vertices are nothing but we can represent as this way, right? So it is v1 comma v2 comma v3 comma v3 comma v4. So this is the representation of vertices. Whereas the representation of edges is we don't have any edges, so it is null. So we can represent it as null. Still we can represent a graph as an ordered pair of vertices and edges, whereas edges is null. That's the only case. But we can still represent it as a graph because it's an ordered pair of vertices and edges. Edges can be null. Okay. So still we can call this as what to say. We can call this as a graph. So from this we can say that minimum number of edges in a graph can be equal to 0, right? So graph can also have 0 number of edges. So the next important thing is, oh, let's understand what is a path in a graph. So what is a path? You can simply define it. Path is a way to move from one node to another node, right? So we can define path as moving from uh, or else a way to move from one node to another node. So it is called as path. So if we call this as node A and if I call this as node B, if I want to move from there to here, we call this as the path to move from node A to node B. So this is the path. So this is called as path in the graphs. And we call a path as simple path if no vertices are repeated. I mean, let's take another example here. Um, so let me add node here, connect it. Okay. So this is called as path. This is node A and this is node B. This is node A and this is node B. Okay, so if we move from A to B, we call it as a path, and we call it as a simple path if none of the nodes are repeated. So if I want to move from A back to A, we can move both the ways. Like if I want to come back to A, the path will be something like this. So we will start from A and we will come back to A. So we are starting here and we are coming back to here. So we encountered the same node twice. So we call that as a path, not a simple path. A path in which no vertices are repeated is called as a path. If any vertices is repeated, we cannot call that as a path. Let's say if I so let's take this example, and if I want to move from this node to this node, I have two ways. Like I can move this way, is a simple path, and this is also a simple path. But if I move this way, so if I do like this, if I move from this node to this node, so if I move from this node to this node and this node to this node and coming back to this node and traversing this way is not a simple path, because still there is a path that is there, but we are encountering the same node twice. So we cannot call that as a path. we cannot call that as a simple path because same node is repeated, so it's not a simple path. So these are different kinds of graphs that we do have, and it's the representation of a graph and the different terminologies that we do have in the graph. Now let's see how to represent the vertices and how to represent the edges in a graph. So it's a simple creation of a class.
Can we like see that next in like next year?
Yeah, sure. It just take a 1 minute so that we can complete this graphs as well. So we will be left with other topics. So it just take a minute. So let
Okay.
me, yeah, not more than that. Sorry for that. So how do we represent vertices and graphs in a tree is, it's nothing but we will just create class heads. So we will create a class head. Inside this class we will create two nodes. So we will create two strings, string start with text and string end with text, end with text, and we will create int weight. These are the three parameters that we do have in an edge, and in the constructor we can assign the values to them. It's a simple thing. So that is nothing pretty much, like we can assign the weight, start and index in the edge. In the similar manner, vertex is something is nothing but a simple node which will have the references. It's, or else you can consider it as an list. In a list we can directly store the vertices as something like this, as a comma b comma c comma d. So that's pretty much how do we store the vertex list and the edge list, uh, edge list, and this is the implementation for the vertices and edges. So for the next session I ask you ask all of you to debug that binary search tree implementation, which is very important. So you try to understand everything: insertion, deletion, and searching the elements in a binary search tree. So that's all for today, and we are almost done with this data structures part. The rest you can just we have other data structures, as I told you. I mean, we don't have nothing much left. All the important things that we have covered: trees, graphs, lists, lists we have covered, and it's vector array list, and everything is similar. And hash tables or something, it's an implementation again back with this lists and all. So you can study them uh, on your own. Like it's simple extension of what we have discussed. The rest are all an extension of what we have discussed, so you can go through them as well. So implementation of a graph, it's simple. It's a simple list, and you can also get them know from the internet or something. You can analyze the implementation of that. We discussed all the theoretical concepts. It's just a Java code implementation. So once you understand the basic linked list implementation, everything is runs on the similar lines. So that's all for today, and we can meet in the next session. In the next session we will discuss that garbage collector and the Java 8 features, like lambda expressions and all. We will discuss in the next session. So that's all for today, and thanks everyone for joining. And if you have any queries, you can stay back and you can ask me right away, or else you can drop off for the day.
Thank you, sir.
Thank you so much.
Thank you, sir.